Hello everyone, in this video lecture we will discuss about the power method. It is an iterative technique used to find out the dominant eigenvalue of a matrix. What do you mean by dominant eigenvalue of a matrix? Suppose A is a matrix of size n by n and lambda 1, lambda 2, lambda n are the eigenvalues of the matrix values of the matrix A, and B1, B2, Bn are the corresponding eigenvector of the matrix A. Linearly independent eigenvector of A. Okay, then lambda 1 is said to be dominant eigenvalue if lambda 1 is greater than lambda 2, greater than equal to lambda 3, and so on, lambda n. Okay, if lambda 1 is the dominant eigenvalue, then it will satisfy the condition that mod of lambda 1 is greater than lambda 2 and lambda 2 may be greater than equal to lambda 3. There may be equal or greater than sign. Okay, but if lambda 1 is dominant eigenvalue, then the strictly greater than sign must be here. Okay, so let us suppose x is a eigenvector that can be written as the summation of ci vi. V is what? That is eigenvector of the matrix A. Okay, as we have discussed here, b1, b2, bn are the corresponding linearly independent eigenvector. So we can express these vector in terms of x. So x is a vector that can be expressed as a linear combination of eigenvectors bi. Okay, now we will operate A over x. So what we are getting? We are getting here A summation of ci bi is a matrix, so it operates over the summation of ci bi as summation of ci a bi. Okay, so I equal to 1 to n. It can be written as, if we are expanding this sum, we are getting c1 lambda 1 b1 plus c2 lambda 2 b2 and so on plus cn lambda n bn. Okay, this is ax. We are getting this condition here. Okay, now if we will operate A again on this equation, then we are getting a square x equal to c1 lambda 1 square b1 plus c2 lambda 2 square b2 and so on plus cn lambda n square b1. Okay, now we will continue this process. So what we are getting? We are getting here ak x equal to c1 lambda 1k c1 lambda 1k b1 plus c2 lambda 2k b2 and so on ck lambda n k bn. Okay, so we are getting this condition. Suppose when lambda 1 is a dominant eigenvalue, that means what is the maximum eigenvalue out of n eigenvalues? Dominant eigenvalues. Okay, then lambda 2 upon lambda 1, lambda 3 upon lambda 1, all these value will be less than 1, since lambda 1 is the maximum. All these value will be less than 1. Okay, as k is tending to infinity, if we are operating a again and again on left hand side, then what we are getting, we are saying like if k is tending to infinity, then lambda I upon lambda 1 raised to power k is tending to 0. Okay, as k is tending to infinity, obviously this term is going to be 0. Why? Because lambda is the maximum eigenvalue and lambda is what? All value will be less than this lambda 1 as k is increasing. So this value lambda I upon lambda 1 raised to power k is tending to 0. Okay, so we can write here some limit k is tending to infinity akx equal to limit k is tending to infinity c1 lambda 1 raised to power k b1. Let us suppose this is the equation number 1. Okay, because all these, if we are taking k is tending to infinity, so all these term will become what? It will be 0. So we are taking lambda 1 k common out of this. Then what we are getting? C1 v1 plus lambda 2 c2 upon lambda 1 raised to power k and so on. So we are getting these conditions, this lambda 1 k, or I should write one more step because that I forgot to write. So this step can be written as, if we are taking lambda 1 raised to power k outside, so I should write here. Okay, this step is what? If we are taking lambda 1 raised to power k outside, then what we are getting? C1 v1 plus c2 lambda 2 upon lambda 1 raised to power k b2 and so on. Cn lambda n raised to power k upon lambda 1 raised to power k bn. Okay, so that's why. So all these value will become 0 as k is tending to infinity. So we can write this condition here like that, a raised to power k, like that. Okay, so a raised to power k x equal to this value. Okay, so let's discuss this. So the sequence, if we go back, then we'll see this sequence. Okay, so the sequence in equation 1 converges to 0. When it is converging to 0, if we go back, then we'll say when it is converging to 0, whenever lambda 1 is less than 1. Okay, if lambda 1 is less than 1, then lambda 1 raised to power k will be what? It is converging to 0 whenever k is tending to infinity. Okay, but it is diverging if lambda 1 is greater than 1. So converging to 0 if mod of lambda 1 is less than 1. Okay, and sequence in equation 1 diverging if mod of lambda 1 is greater than 1. Okay, provided C1 is not equal to 0. So this is the condition we require. Okay, so now the thing that you should understand properly, the entries in AKX, like if you see back, then the entries in AKX will grow with K. Okay, if K is increasing, so obviously the entry in AKX will also increase. So the right hand side is going to be 0 whenever mod of lambda 1 is less than 1. Otherwise, it is diverging or it is going up to infinity when lambda 1 is greater than 1. So ultimately what we are getting overflow and underflow problem. Okay, so to take care of these things, we scale the power of akx. Okay, so to take care of this possibility, what possibility? The problem of underflow and overflow. Okay, so to take care of this possibility, we scale the power of akx. Okay, in an appropriate manner to ensure that the limit is finite and non-zero. Okay, so the limit is finite and non-zero. So unit vector x0 relative to infinity norm for the vector. Let us understand this method mathematically, and so write the working rule of power method. We will assume, so step 1 is what? We will assume an initial vector x0, that is the initial guess, also initial guess, or we'll say initial vector. How to take this initial vector? We can take generally initial vector that is containing all entries as 1 1 1. Okay, second step is what? We will find out y1, that is equal to a x0. Okay, after choosing this y1, what we do? After choosing this x0, what we do? We will operate a on x0 and then we'll get a vector y1. Then compute maximum value, let us suppose p, or let us suppose any value. Okay, let us suppose p. P is what? That is maximum of y1. That is the, and find out the maximum entry in vector y1. Okay, that we can take as the first approximation to the eigenvalue. That is the first approximation to eigenvalue. Okay, now third step is what? After that, what we do? We will compute x1, that is the first value, that is the next approximation to the eigenvector, that is what? y1 upon lambda 1. So this is the process is called scaling. Now we are scaling our vector. So we are scaling our vector. So this is the step that is important, that I discussed previously, that at each and every step we will apply scaling. So lambda 1 is the maximum value in y1. Okay, so what we do, will divide the whole vector y by the maximum value. So the maximum element will be what in y1 now, or in x1 now? That will be 1. Okay, and the fourth step is what? The fourth step will be your, so the fourth step will be what? Now compute y2, that is what? A x1, and continue this process. Continue till you are not getting desired accuracy. That means, how to check desired accuracy? That means we will compute lambda 1, lambda 2, lambda 3, like that. Lambda, continue till we are not getting lambda n plus 1 minus lambda n desired accuracy. Okay, so this is the working rule of power method. Let us do one example, then it will be more clear. Okay, so let's discuss. Okay, let us explain this example with the help of power method. Let us explain this method with the help of this example. So let us suppose a matrix is given to you whose dominant eigenvalue we have to compute. There will be two eigenvalues since the order of the matrix is 2, and I am interested to compute dominant eigenvalue of this matrix. So how to do that? So let us take initial vector as 1 1. Okay, so this is your, so what we do, we will compute y1 equal to what? That is a x0. So a is your matrix 2 3 4 10, and you will multiply by 1 1. What you are getting? You are getting here like 5 and 14. That is the first iteration we are getting. Now what we do, we will compute maximum value. Let us suppose yp, that is the 14, and after that what we do, we will divide y1 upon p. Okay, this p is your first approximation to the eigenvalues. So that is what you are getting here, 5 upon 14 and 14 upon 14. That is 1. That is coming out to be 0.35714. Okay, 0.3. Okay, and the value here 1. Okay, so this is the value we are getting here. So now we can write it here like that. A x0 that we computed equal to lambda 1 x1. So what is your x1? X1 is this value. So we can write, and lambda 1 is what? That is your 14. Okay, so that is 14, 0.35, 7 1 4 and 1. Okay, so this is your, this is the first approximation to the eigenvalue, and this is your eigenvector that we are calling it x1. Okay, now do the second iteration. What is second iteration? A x1 that we are calling it y1 equal to a x1. Okay, what is a? A is the matrix same 2 3 4 10, and x1 we computed here 0.35, 7 1 4 and 1. Okay, then compute y2 equal to a x1. So what is the value coming out to be here? The value is coming out to be here as 3.71429, and the second value is 11.42857. Okay, that is your y2. Now the maximum value is what? That is 11.42857. So that is the next approximation to your eigenvalue, that is your lambda 2. And the vector what we are getting here, so we are taking it common. So what the value we are getting in the bracket, that is 0.325 and 1. So the maximum value we are having, this is the maximum value, so we will divide it by this value. So what we are getting here, that is your x2. So this is the next approximation. Okay, now third iteration. So we will compute y3 equal to a x2. Okay, so y2 is what? That is we computed, and we are writing a x1 as lambda 2 x2. Okay, so this x2 is your eigenvector for the next approximation or for the next iteration. So we will use it and compute next approximation to the eigenvalue. So y3 equal to ax2. Okay, so what is coming out to be here? Now you are getting here 3.65, and this value is 11.3. Okay, so now we will take common this element. This is the maximum element, so we will write 11.3 here, Okay, so what we are getting here, 3.65 upon 11.3. So the value is coming out to be 0.32301, and this is 1. Okay, so this is this is your lambda 3, and this is your x3. Now we will compute fourth iteration. So what we are getting, y4 equal to ax3. So A is what? The matrix, given matrix, and x3 is what? That is the vector that we computed in the previous step. So what we are getting here? We are getting here 3.64602, and this is 11.29204. Okay, so what we are getting here, we will divide it by maximum value, that is 11.29. 11.29. Value is what? It is coming out to be 0.3228. 32288. Okay, so this is what? This is your, since in the question asked to compute 4 iteration, so this is according to the 4 iteration, that is the dominant eigenvalue. This is the dominant eigenvalue. And this is the corresponding dominant eigenvector. So this is the power method that we discussed here for this example. Okay, thank you.